Good afternoon. Welcome to this session on carbonaceous aerosol emission sources and their importance to air pollution in India. So here we will try to discuss evidence for impacts of carbonaceous aerosol sources on air pollution in India, what we know about the scales of impact, whether it is city, whether it is region, etc., and then what recommendations we may make for interventions and mitigation priorities. I'd like to thank Professor Sachidanand Tripathi and the NCAP NKN partners for this opportunity to share our work. So to go ahead then, what are carbonaceous aerosol emission sources and what is the implication to the mortality risk from ambient particulate matter? So as we've seen from the what's called Global Burden of Disease study, which is released every year, what we are seeing here is that among various risk factors, high blood pressure, diabetes, hypertension, smoking, etc., ambient particulate matter is the third highest ranking risk factor in increasing the mortality due to various diseases. And what are these diseases? If you look at dark blue, that is chronic respiratory disease. If you look at light blue, that is cardiac diseases. And if you look at this orange, it is lower respiratory infections. It also says diarrhea, but it's lower respiratory infections. So really half of the disease burden comes from worsening of the heart diseases and the lung diseases. And of course, we know that National Clean Air Program aims to cut PM 2.5 pollution by 20 to 30% by 2024 over 2017 levels. So how might we build evidence? I know that, and we all know that NCAP has really proposed a large enhancement in the measurement system. And one of the ways in which we utilize a combination of measurements and models is to have a network here to develop emissions inventories, and this is called the bottom-up approach, deploy them in various models to simulate air quality. We can do this by turning off source by source so that we are simulating the fraction of ambient PM 2.5 due to each source, estimate health impacts and so on, but basically then have very clear recommendations for how do we start with emissions inventory, go to air quality modeling, integrate it with measurements, and then come up with important mitigation strategies. So one of the things that we've looked at in improving emissions is to build what is called the Smog India Emission Inventory and Assessment Platform. And this has been built over almost 10 to 15 years at IIT Bombay and is now being expanded under what is called the NCAP Coalesce project. And this is National Carbonaceous Aerosols program, also from Ministry of Environment. And in this, what we do is produce gridded emission files over India, covering all the different sectors, which is, if we see power plants, industry, transport, distributed diesel generator sets, pumps and tractors, as well as residential biomass, cooking, brick production, open burning, agricultural residue, etc. All the sectors are present here. And based on emissions modeling, we are able to then say what are the baseline emissions. How much of primary PM 2.5, its constituents like black carbon, organic carbon, and its precursors for secondary PM 2.5, like SO2, NOx, and VOCs are being emitted. We're also able to make future scenarios and say, if we had interventions at a particular level, how might emissions change? And if we have a very ambitious scenario, which is shown here in triangles, can we really reduce the emissions strongly? Then when we deploy this is called assessments in air quality models, we can see that we are able to estimate how much of pollution comes from where. So just very quickly to say that this is underpinned by a lot of um, sort of careful and rigorous modeling, as well as uncertainty estimation. And so what we say here is that for any sector, which can be, as we said, residential, industrial, etc., we have to know the fuel consumption, which is the fuel type, and the combustion technology. That is why this is called technology emissions modeling. What we're saying is, if we're burning coal in a pulverized coal combustion boiler, you have a different emission than if they are burning it in, let us say, a stoker, or if we're burning it in a sigri or a chula for cooking. So with this kind of technology linkage, there is another thing here, which is activity rates production, which, in sectors like transport, it becomes very complicated. A has a whole story behind it, which includes what is the number of on-road vehicles of a variety of types, whether two-wheelers, three-wheelers, heavy-duty, light-duty. How much are these vehicles traveling every year in terms of kilometers traveled? And then what is the fuel efficiency and the emission factors? And this is just saying how we might estimate uncertainty and propagate it, etc. So with this kind of idea, in the NCAP Coalesce project, which is coming to an end in 2023, about 22 institutions have collaborated, among which 15 have been involved in the emission inventory development exercise. And now we have over 25,000 nationwide surveys in residential sector, in the non-cooking, which is lighting, water heating, which are residential activities, in agricultural residue burning, fired clay brick production, and on-road transport. And then the other sectors, power plants, formal, informal industry, diesel generator sets, etc., are also included. And what this is basically saying is that a large amount of new primary data, along with secondary data, are then packed into a calculation framework, wherein we are able to then put out these maps, and we're hoping to be able to give the gridded emissions at 5-kilometer grids over India and for all over India. So with this kind of improvement in reducing uncertainty, in increasing accuracy in the PM 2.5 and its precursor emissions, we then pack it into a decision support system. Here it's just showing that there is a database, there are survey data, there's secondary data, government reports, the emission factors from measurements, spatial proxies, which are very important to get the spatial distribution right, and various kinds of programming that is needed to essentially take it to the final product. And here we also see that this becomes an emissions management system, and we can update it for future years. So that is the overall goal here in producing this emission inventory. So then, using this, what might we do with simulations? And here I think I'll quickly go through this. We don't really want to dwell a lot, but the models are based on fundamental treatment of transport equations, which is to do with momentum transfer, energy transfer, and continuity, and then species continuity, which says, that there is wind, which is advection, there is diffusion, both molecules as well as small particles, there are emissions, there's reactive loss, deposition. All of this is brought into the model. Again, what we have is, this idea that we have to now calculate it not at one location, but at grids. And these grids can be limited over India, they can be global, and even if you're limiting over India, you have to have boundary conditions from global models. And so what I'll discuss is full India simulations. One can have a much finer grid for a particular city nested within these grids. So this is sort of how do we discretize it spatially, and we discretize it also in time. We want to calculate the movement of pollution, the chemistry, the emissions and deposition sequentially. So we are not doing them all together. So with this kind of idea, the question is, there is WRF Chem, WRF CMAT, WRF Chimere, there's GeoSchem, there's, Reg CM, there are various models. So if we pick up a model and we just run it over India, are we going to get the correct result? And the answer is definitely no, that's not the case. And so we have to do a great deal of optimization. We have to do optimization, data assimilation of the observed meteorology, as well as, what we find is this simulation itself in terms of optimizing boundary conditions, etc., etc. So then this is what we have. And what we're showing here is that the emissions, of course, have been customized for India. If you take global inventories, you will typically underestimate by factors of 5. It can be factors of 2 to 5 or 6 underestimation. So only 20% of the actual level is being simulated. We have to optimize the dust transport, how much dust is coming in from the different boundaries, as well as assimilate meteorological data and find out which are the best options to simulate air pollution as well as regional climate over India. So with this idea, we are, then trying to look at how we might do model evaluation. And this is a rather complicated slide, but all I want to say here is that the model is very carefully evaluated, both to do with satellite detections, like with aerosol optical depth, again, between MODIS, MISR, different kinds of sensors, and with the large now database available of CPCB ground-based measurements, as well as with chemical composition wherever it is available. You can see here, orange is black carbon, yellow is organic carbon, green is sulfate, blue is nitrate, and purple is ammonium. And these are evaluated at multiple cities across India. So one of the sort of achievements in doing this big optimization exercise is that the annual mean PM 2.5 concentrations, when evaluated against about 75, 80 station measurements across India, the model is only underestimating by 10%. So it is a normalized mean bias of the order of minus 0.1. And that is actually a very good achievement because, as I pointed out, the underestimation is often factors of 2 to 5. But again, I would like to point out there are larger seasonal underestimations in winter and summer. And the species, the largest underestimation is for organic carbon, which runs about 2 to 3, while the other species are being calculated closer in terms of being able to evaluate. So this is at the ground, and this is, Swami was an aircraft campaign data with Ministry of Earth Science and with UK collaboration, and we do the evaluation both at whatever is the aircraft campaign heights as well as the ground level. So after these evaluations, we may basically be asking, how does pollution change? And this is a study that we participated in, where basically in all the studies I will present, it is smog emissions from IIT Bombay. In some cases, we do the simulations ourselves. In some cases, simulations are done collaboratively. Another group does them. And here we are asking the question, how much can we reduce the pollution going till 2050? And what is seen is that unless we have very, very ambitious scenarios, which includes 100% shift from chula to cleaner fuels, whether it's electricity and induction stoves, whether it is LPG, 100% shutdown of agricultural residue burning. So these are the kinds of scenarios that are required in order to achieve very low, future emissions. So then where does air pollution in India come from? This is surprise number one, perhaps. The important message is that air pollution comes from human emissions. Anthropogenic sources contribute greater than 60%. So less than 20-30%. Green blue is from natural sources, wind-blown dust, but most of it is from our human emissions. And the surprise is the largest single contributor is biomass cooking in residential sector. So to look at this a little carefully, residential biomass, open burning of agricultural and grassland fires, and fired brick production. Note here, the scales are different. It's 50% here, 35 here, and 6 here, so that they're all visible. They add up roughly to half the PM 2.5 levels over India. While industrial coal, power plant coal, distributed diesel, and transportation add up to actually close to about 40%. So what we're saying here is that there is a large number of both these carbonaceous aerosol sources. We also call them non-formal sectors, which are contributing to air pollution, which we need to address very urgently. Here we are showing the state picture 2015 and 2050. In 2015, except for 6 or 7 states, all states are in violation of 40 microgram per meter cubed yellow, which is the National Ambient Air Quality Standard. If we do very, very ambitious mitigation by 2050, most of the states, except for maybe 10, can be brought under the National Ambient Air Quality Standard. However, it's a bit discouraging that the states which have still higher than the standard also have large populations. Then the other question we asked, this is a different model, and we ran these simulations in IIT Bombay, where we're basically saying that if we turn the carbonaceous aerosol emission sources on and off, we once again do an evaluation. All the models agree quite well with each other, which gives us confidence. And we find that in October, November, December, January, February, lot more reds and yellows, which means that the pollution, particularly in North India, is much higher than the annual mean. And what is the contribution of carbonaceous aerosol sources? That's the green, which is being shown for Northern India, for Peninsular India, and for rest of India. And it's rather startling that these carbonaceous aerosol non-formal sources are contributing 60 to 80% of the air pollution in northern Indian states, which we can see over here. And it's not that much different, 40 to 70%, somewhat lower in the rest of India. So what this is saying in terms of implications for NCAP is we urgently need to expand mitigation priorities to include residential, agricultural residue and waste burning, fired clay brick production, and on-road diesel transport as very important interventions beyond the city scale of what actions are being proposed at present. Another sort of study where we collaborated, and the question that we asked is, if we have regions, Northern India, Indo-Gangetic Plain, Western India, Central India, Southern India, the emissions from each region, how much are they contributing to the air pollution in the region, and how much are they contributing to a different region? And here OI is outside India, which means that there's also some pollution which is coming in. The brown part is coming in from outside India. What is very startling, of course, is Indo-Gangetic Plain has the highest amount of pollution and the highest population, and that is something which is now becoming very well known. But an interesting thing is, each region, of course, contributes the most to its own pollution. So orange to North India, green to Indo-Gangetic Plain, yellow to Eastern India, etc. But Indo-Gangetic Plain, bright green, is contributing air pollution to every other region in the country, including Southern India, where maybe 10 to 15% is coming from the IGP. So then let's quickly take a look at where are the human health impacts and are they limited to cities? So in order to just save time, I will very briefly say that health impacts come from these relative risk curves, which are developed with data that come from everywhere in the world, including Indian data, on how much is the risk enhanced. And what we find over here from the original study I had shown you is that there is a high, what is called premature excess mortality. How much additional deaths are likely to be there because of air pollution and from different diseases, lower respiratory infection, pulmonary disease, stroke, ischemic heart disease, etc., etc. And what we find is when we reduce pollution, let's say the 2050 scenarios, we do reduce the mortality. But unfortunately, the mortality, even in the best scenario in 2050 S3, is larger than 2015, which is at this level here, because of an increasing and aging population. So we really need to really have ambitious mitigation measures. I think we can skip this in the interest of time. So who is experiencing the impacts? In order to, kind of look at that carefully, we tried to look at the spatial distribution of urban and non-urban areas by looking at a satellite detection of what is called nighttime light. So the satellite sensor, when the light is bright, says it is an urban location. When the light is below a brightness threshold, it's classified as a rural location. A non-urban location at 5 kilometers all across India, which is a very fine sort of scale on which to do this. And with the same kind of, simulated concentrations, what we find is surprising. Almost 70% of the excess mortality is not in the cities, it is in the rural areas. This is again shown here, which is the orange, which at every 50 microgram per meter cube, 75 microgram per meter cube, 100 microgram per meter cube Orange, which is non-urban population in millions exposed to that level, is much higher than the urban population. So where does Delhi and all these very highly polluted cities fall? Above 150, where the urban, which is green, crosses over and is above the rural orange, this is where these cities fall. And so, our takeaway here is our focus has been a little too much only on the cities, while two-thirds of the effect is being borne by our rural fellow citizens. So we need to expand the intervention scales over here. Okay, I'm going to try and forward my slide here. And let us just skip this again in the interest of time and just say we have many capacity building needs here, from curriculum to modeling courses to air quality management tools, which we can spin off from research, to have commercial air quality management services, whether it is with HPC companies, software companies, consulting companies, and think tanks. And then, of course, build the stakeholder interface. And to finally finish, I will just dwell on two recommendations here for NCAP. That is, the scale of intervention has to be expanded. It's imperative to expand it and have implementation on regional, which is state and district scale, in addition to the city scale currently being planned. And mitigation priorities, there's urgent acceleration of residential agricultural waste management and brick sector mitigation, along with the ongoing plans for city action. So thank you for your time, and we look forward to questions during the question